So we are starting with the last lecture today, well, after which we'll still have a tutorial. In this lecture, we start the topic on Ethereum. So this is a topic that spans over 2 lectures. The second lecture will be tomorrow. So Ethereum is, of course, yet another cryptocurrency. However, it plays a special role because it's one of the most secure ones. It's also second after Bitcoin in terms of the market cap. So, it also includes a lot of interesting technological elements, which is why we spend more significant time dedicated to that cryptocurrency. So, I'll use quite a few different materials for the lecture today, but above all, I'll be using the paper called Understanding Blockchain Definitions, Architecture, Design, and System. So first, let's start from background on Ethereum. It's managed, well, Bitcoin is managed by Bitcoin Foundation. Ethereum is managed by Ethereum Foundation, but it includes, it's an industrial consortium, which includes many industrial players and enterprises such as Toyota and Microsoft. Its focus is on creating an open source and flexible platform. And of course, by platform, I'll soon explain what I mean by platform, as opposed to just cryptocurrency. The cryptocurrency it's using is 1 Ether. So is Ether, and 1 Ether is equal to e to the 18th of Wei. So Wei is a much smaller division of the Ether cryptocurrency. As of now, 1 Ether is equal to approximately 1863 US dollars. But of course it varies over the time. It came up with the idea of smart contracts and Ethereum virtual machine, which we will be covering. And it is permissionless. Initially, it was using proof of work, but later it switched to proof of stake. Later recently in 2022, so it was deployed in 2013, and from 2013, like 9 years of proof of work, from 2022, they switched to proof of stake. Ethereum, in addition, Ethereum has limited support for permissioned ledgers. So, in addition to the main public deployment of Ethereum, there are many proprietary deployments. So how did it all start? I was already covering this topic in the beginning. It started from a proliferation of Bitcoin spawn-offs. And then people are also, so why so many different spawn-offs? Because people realized that digital currency is not the only electronic object of value. So we could also store documents. Additionally, people wanted to support extended financial applications such as crowdfunding, which was not possible on Bitcoin. People wanted to support multiple-party escrow transactions, where there would be like one trusted party within the transaction, only for that particular transaction. And in order to support that, there was a need to extend Bitcoin in a certain way. And as a result, we ended up with hundreds of Bitcoin spawn-offs. And then Ethereum envisioned that a single platform supporting all different extensions is better than 100 of specialized systems. So that's why we call Ethereum a platform, unlike Bitcoin. Okay, so what was the innovation in Ethereum? It provided a verifiable Turing-complete script language. As a matter of fact, it came up with the idea of Ethereum virtual machine. So it's like Java virtual machine for those of you who know Java. Every instruction in Ethereum is executed on a virtual machine. So every instruction may have a cost associated with it. It's all standardized. And no matter which operating system, no matter which client, every transaction consists of a set of instructions. It's like more or less like assembly code. And every instruction is executed on the same virtual machine, and it's verifiable. Okay, so additionally, of course, like virtual machine, instructions of virtual machine are in low-level language, right? So that's not the language in which we want to program. Therefore, there are many upper-level languages for developing smart contracts, and of course there is a compilation from the smart contract languages to the language of the virtual machine. And then Ethereum also provided templates for the scripts. Another interesting critical distinction from Bitcoin is that those scripts can be stateful, with the state stored on the chain, and significant amount of sophistication in Ethereum went into the question of how to store the state. And today we will be covering this question. And of course, later, as I was explaining in the lecture on the evolution of blockchain, the idea of this platform gave rise to distributed autonomic organizations and the application ecosystem of applications developed on top of Ethereum. So the analogy that Vitalik Buterin, who originally was the author behind Ethereum, was to use the Swiss knife analogy. It's a knife which you can see with so many different tools, but all combined within a single knife. So let's compare Bitcoin with Ethereum. So what are transactions in Bitcoin? It's just a transfer of Bitcoins. What a transaction in Ethereum is more complicated. In addition to transfer of Ether, we have a creation of smart contracts. We have internal transactions. We have specialized transactions for contract calls and so on. Regarding the accounts, other accounts in Bitcoin, no. There are additionally wallets which are like external to Bitcoin itself, but which are used in conjunction with Bitcoin. And okay, what about Ethereum? In Ethereum, there are accounts. There are two types of accounts. One type is accounts that belong to human users, and another type of account is account that belong to mechanized or rather automated smart contract. So each smart contract, a script in Ethereum, may have its own account, or even multiple accounts if you want. Transaction fees. In Bitcoin, the sender of a transaction decides how much fee to pay to the miner. In Ethereum, it works differently. First of all, Ethereum uses gas. So let's take one step back and let's talk about the concept of gas in Ethereum. So in Bitcoin, a script is just some very small program with the limited computation, and therefore use of resources by scripts, by executing those scripts in Bitcoin, is not a significant issue. In Ethereum, a smart contract or a script is like a full-fledged program. It may have loops. It may have functions, so one function calling another. So can you immediately see the challenge resulting from this? So what would be the challenge in Ethereum? If you start running full-fledged programs. Well, the question is who tests those programs, who debugs those programs? What if someone inadvertently or as an attack would write an infinite loop? So now every single node, so every single node needs to verify every single transaction. As a result, every single node will perform infinite loop. Like all nodes in the Ethereum network will spend significant amount of resources on that, right? So of course, like we need better scripts. Of course, we need better scripts. How do we make sure that the scripts are good? So the solution adopted in Ethereum was the concept of gas. Every script pays for its execution. How? Well, the scripts consist of instructions at the level of Ethereum virtual machine. So each instruction has an execution cost associated with it. And what happens is that every program in Ethereum has a budget for execution. And as the program is being executed, after each executed instruction, this budget is being decreased. And that happens until the budget reaches zero. If the execution finishes before budget reaches zero with a positive budget for the script, then the execution would be successful in that regard. If, however, the budget reaches zero, even in the middle of the execution, then the execution would be immediately aborted. It's a problem of the script. So if someone wants to run the script to be successfully executed, that someone would need to provide sufficient budget for the script. And the budget is the gas. So one could say that while executing scripts are burning gas. Okay, so coming back to the question of the fees. In Ethereum, the fees are not specified by the sender. Instead, well, essentially there is no need for fees because the payment is for the execution of the transaction. And it's calculated based on the price of gas, right? So the price of gas may also vary over time. And it's calculated based on how many instructions were executed on the Ethereum virtual machine. So it's not specified beforehand. It's calculated after the execution. Block content. So what does a block consist of? Well, we already covered this question in Ethereum, in Bitcoin. In Bitcoin, there is a block header and there is a block body. And the block body is essentially a tree, or well, it's a list of transactions, which those transactions are organized in a Merkle tree. It's more complicated in Ethereum, mostly because we need to store the state. So in Ethereum, there is a transaction tree, which is pretty much similar to the transaction tree. However, there is also root hash. There is also like a tree for the state, and there is also a tree for the receipts. I'm going to take a dive and speak about both the state and the receipts soon. Okay, next, what is the state in Bitcoin? So in Bitcoin, we need to keep track of unspent TXOs, right? In Ethereum, we need more. We need to keep track of the accounts, both user accounts and public accounts. We need to keep track of the receipts, and the scripts are also like a program, so we need to make sure that those programs have not been tampered with, right? So there could be some significant code involved. Querying the ledger. So in Bitcoin, the main purpose of querying the ledger, either you download the ledger and verify all of it, or you verify inclusion of a transaction, which is simple for a full node, but which takes the simple payment verification procedure for the lightweight nodes, which only keep the headers. Ethereum. In Ethereum, querying is much more sophisticated. So we can ask for the balance of a particular account. We can ask for local proof for events, transactions, and more. So this gives you, like, I have not given you details, I'm going to go deeper, but this gives you an overview how Ethereum was advancing the field compared to Bitcoin. So what are the new conceptual elements in Ethereum? When Ethereum was using POW, it was using a different mining algorithm to prevent ASICs. It's not relevant so much now after Ethereum switched to proof of stake, but to date, Ethereum switched to validators and proof of stake. As mentioned, Ethereum came up with the idea of smart contracts. Well, okay, it's exactly true. With the idea of smart contracts was again from the 90s. But Ethereum was the system which came up with the idea of integrating smart contracts within the blockchain. And by the way, smart contracts, so I was talking about gas. I mentioned, like, you pay for the execution of instructions. That's true. Well, you additionally keep for storage. You additionally pay for storage. So there is another element of payment in Ethereum. Like, you store, the smart contract stores information, it needs to pay for the storage. So Ethereum is not using UTXO at all. It doesn't have the idea of those individual tokens with values. Like Monero does, Bitcoin does, not Ethereum. Ethereum has balance like a bank. So for example, Alice receives 10 different transfers. All those transfers would not be kept separately. They would be consolidated in a single account that belongs to Alice. Okay, more. So please remind me which consensus rule is or conflict resolution rule is used in Bitcoin. We talked about it in the lecture on Bitcoin. So what's the name of the rule that's used to resolve conflicts and reach consensus in Bitcoin? If we have several branches competing with each other, how did we select the best branch? The winning branch? Please speak up. With the longest. So we were selecting the longest branch. That's the rule in Bitcoin. Ethereum uses a different rule, and there is a good reason for that. The rule in Ethereum is called the LMD ghost rule, and using this rule, Ethereum is able to provide faster transaction confirmations. So we are going to talk about the differences, of course. And of course, as mentioned, Ethereum uses different storage solutions, including state storage, but there are also other significant differences with regard to how the data is stored on Ethereum compared to Bitcoin. All right, so Let's go over different elements. Transactions in Ethereum. This is how transactions and blocks in Ethereum look. So this includes block header, or similar to body, transactions. However, the transaction includes several fields. It includes the gas price. Gas price is like how much the sender of the transaction is willing to pay for the gas, because as mentioned, the gas price is also variable, and there is negotiation about the price of the gas. If the same transaction is executed at different times, like in a year from now, I'll be issuing same transfer, I may be paying different amount for the gas. So price is how much the transaction is willing to pay for the gas, for the unit of gas. There is a recipient. So Ethereum does not care about traceability. It just puts the recipient. Now we have account, so it can put the target account of the transfer inside the transactional structure. Of course, the amount, signature, so that's the same, but it also has some interesting different fields like account nonce, which has nothing to do with the nonce of POW. It's something used to verify the account. Let's talk about proof of stake and validation of blocks in Ethereum. So every node in Ethereum can become a validator by staking certain amount of Ether. Now, the assignment of validators and block proposers is done on the per epoch basis. So Ethereum divides time into epochs of time, where each epoch takes 6.4 minutes. And each epoch is further divided into time slots. Specifically, so 6.4 minutes are divided into 32 slots, 12 seconds each. And the validators and block proposals are selected on a per slot basis. And the way it's done is again using a pseudo-random assignment. One validator becomes an appointed block proposal, while the other validators for a given slot become attesters, so they verify the correctness of the proposal. And the assignment is such that all validators are designated to serve as attesters exactly once per epoch, not per slot, per epoch. And all attesters are assigned to a given slot, are split up into many equal-sized committees. So there is a rule to have minimum 128 attesters in each committee, and minimum 164 committees per slot. Minimum 1 committee per slot, maximum 64 committees per slot. So thanks to these rules, we can calculate the minimum of validators required for Ethereum to operate. So we need to have minimum 1 committee per slot, and we need to have minimum of 128 attesters in each committee, which means that we need to have and then we have 32 slots for each epoch. So attesters are never used within the same epoch, and therefore we require a minimum of 128 times 32 equal to 4,096 validators. The same validators can be reused across different slots. So for the next slot, we could use the same set of validators, or we could use different validators. But within, for a different epoch. But within the epoch, we are not allowed to reuse attesters. Okay, so what's the situation today? Today, instead of the minimum of 4,000 validators, we have over 1 million validators. So it's not about the minimum, it's about the maximum. The maximum of 64 committees has already been reached. In addition to validators, we have aggregators. Aggregators are validators that have some additional duties. Namely, they participate in the dissemination of the blocks. So those are the rules about the committees and proof of stake in Ethereum. So again, one could say, so why would anyone want to become a validator? So the proposal, the block proposer gets a reward similar to the reward in Bitcoin. The validators also get some smaller rewards. So this is why everyone wants to become an official validator, official attester. And of course, like everyone else, apart from the official attesters, can also validate the ledger. The ledger is open to all. The attesters do not get any significant additional information about the ledger, but they get a reward for officially attesting the blocks. So the switch from POW to POS in 2022 significantly reduced energy consumption, also reduced transaction fees and cost of gas, because now it's cheaper to execute transactions. There was a fear of increased centralization, because now, of course, like not everyone gets to become a validator. You need to stake some amount. And there was a fear that basically only a selected few participants, nodes in Ethereum, could become validators. And that would result in a centralization. So far, as you can see, there is over 1 million validator nodes. So that's good, in the sense that the centralization fears did not come to be supported in reality. Okay, so that was about POS and validation. Now, as I promised, the conflict resolution in Ethereum was different compared to Bitcoin. So instead of the longest branch, we are selecting the heaviest branch. What do I mean by that? So here you can see branching in Ethereum. Well, in the past, here it's vertical. It starts from Genesis at height 1, block at height 2. Start with the branching. Two alternative versions at height 3. And here, like, under this version of block 3, there are 3 different versions of block 4. Under this version of block 3, we have just one version of block 4. But at height 5, here we have repeated versions. So we have nested branching. Okay, so how do we select the winning branch? The longest branch is clearly this one, right? It's not the winning branch. So in order to select the winning branch, we compute the amount of blocks under a given branch. So the amount of blocks, the amount of also the amount of transactions. So here we have, here it's 1. This one combines with 2, 1 plus 2, 3. still free. Here we have like 3, because there are 3 transactions here. Here we have 5. This one is 5 plus 3, 8. So we calculate the weights based on the amount of later blocks. And then we select, if there is a branch, we select the version of the block with the biggest weight. So here is this one with the biggest weight. And then we have several alternatives here. We select the one with the biggest weight, choose 3, not the longest one. So it has been shown. Okay, so what's the big idea? Why do we want to do that? Because this way, the winning branch is secured by high amount of the same idea. By the way, is applicable both to proof of work and proof of stake. So it was the same idea, and the idea is that the winning block is secured by high amount of work or high amount of stake. So it's more difficult. It's more difficult for the attacker to overcome the weight than it is to overcome. So in case of branching, the main chain is secured by a high percentage of blocks, which is also called the mining utilization, the metric which we looked at when studying Bitcoin energy. The mining utilization is high in Ethereum compared to Bitcoin. Go ahead. Good question. In this case, in this case, we may select. Okay, so usually, I mean, it's the same question you could ask about Bitcoin. What happens if 2 branches have the same length? Okay, but we considered that question indirectly in the context of Bitcoin. So what would be the answer in the context of Bitcoin? What happens if 2 branches have the same length? Exactly. Exactly. It's a transient answer. It's a transient situation. It's only a temporary situation. If we have 2 competing branches with the same length, then there was a slide about that. Some nodes would continue mining on top of one branch. Some nodes would continue mining on top of the other branch. So eventually, because of the variance, one branch would be extended faster than the other branch, and the symmetry will break. And the same true. Okay, so in fact, like this idea of okay, like why is it called Ghost? It came from the Ghost protocol, and the Ghost protocol is actually quite relatively old. It's also from 2013. So the idea of using this conflict resolution rule is something Ethereum came up with from the beginning. It's not new due to the proof of stake. But the same concept is also applicable to the new Ethereum using proof of stake. So As a result, Ethereum is more secure than Bitcoin if we assume the other like the same configuration parameters. However, they are not the same. Thanks to higher security and the ability to tolerate branching better, Ethereum reduced the average time to produce a block. So in Bitcoin it's 10 minutes. In Ethereum it's about 13 seconds. And of course with 13 seconds Ethereum gets much more branching than Bitcoin with 10 seconds. But it's able to tolerate branching better. Okay, so this was about the conflict resolution rule. The next question we are going to consider is that of blockchain storage and its organization. So in Ethereum, we have a chain of blocks which is stored in files on disk, but additionally, the storage includes a key value store for keeping auxiliary information related, for example, to the system state. And with emphasis on the state storage and state-related operations, such as we can search for the state, this emphasis results in more complex storage mechanisms compared to Bitcoin. So the balance of roles between the chain of blocks and the key value store is fundamentally different in Bitcoin and in Ethereum. In Bitcoin, we never search for we never need to search for specific bits of information. And if we need to search for blocks, it's conducted mostly using the chain and not the key value store. While in Ethereum, the reverse is true. In Ethereum, all information that is stored in files on disk is also duplicated in the level DB key value store. For example, we keep block headers and transactions in level DB key value store. And the key value store is the main storage element used in the search. So the storage on disk of individual blocks on disk is not as important in Ethereum as it is in Bitcoin. And another significant difference is that Ethereum doesn't use Merkle trees. It uses a modified version called Merkle Patricia trees. Why? Because that kind of structure is also good for Merkle tree is only good for cryptographic verification. It's not used for searching. But Merkle Patricia tree is also used for searching. So here's an illustration, right? So we have a block, which is also, and we also have the database. So in the block, we have proof of work or proof of stake related information. We have, like in the header, we also have the hash pointer, the secure pointer to the previous block. That's the same. But then we have different trees. We have transaction tree, which is similar to Bitcoin, but we also have state tree, and we also have receipt tree. So now it's probably a good time to, okay, so transaction tree contains all transactions in the block structure as Merkle tree, so the same, but there are some including, for example, the gas price. Then we have a tree, Merkle Patricia tree, for storing the state after all transactions are set, and we calculate the root hash and we store the root hash also in the header. We have a third tree, which is a receipt tree. What are receipts? We log out the outcome of each transaction, and we sign the outcome, the output of each transaction. And that is like the receipt. The receipt shows, yes, I have executed the transaction, and this is the output of the transaction. So those receipts are also verifiable stored, and it can be verified in Ethereum. So let's talk about Patricia trees. Unlike fixed transaction history, the state in Ethereum is frequently changed because new accounts are inserted and old accounts are deleted all the time. So we need to maintain the state. And additionally, the state of an account needs to be searched. So the Merkle Patricia tree is the structure which can support all those operations because it provides logarithmic complexity for search, for insertion of new data, for updating the data, and for deleting the data. In addition to efficiently constructing Merkle proof. So similar to the Merkle tree, data items are stored in the leaves. However, unlike Merkle tree, Merkle Patricia tree is a prefix tree, which uses hashing mechanism to produce a key string that determines the path of the data item within the tree. And in Ethereum, the key is encoded as a hexadecimal, so the vertex has a number of children which doesn't exceed 16. Let's take a look at an illustration. Imagine that we have two data items. For example, two transactions or two state elements, two accounts. And imagine that one data item is hashed to the value of ABCD, and the other data item is hashed to the value of ABEF. So, what is a prefix tree? In a prefix tree, we'll be building a tree based on those values. So ABCD and ABCD, and then in the leaf we'll store the item which hashes to ABCD. And then ABEF, and in the leaf we'll store the item which hashes to ABEF. Okay? So this is how the prefix tree would look. Now, Merkle Patricia tree is a classification called the compact predict tree. So instead of having many levels, the tree will be compacted to A node, and then CD node, and EF node. So it's the same case, but different representation, more compacted. And this is the one, the compact predict tree is the one used in Ethereum. And it's used for pretty much everything, like accounts, balances, and so on, as we'll see soon. So the trees are stored in a database, as mentioned. Each vertex of every Ethereum tree is stored as a separate record in the level DB storage, which is again a key value storage, and the record key is derived from the hash. Additionally, the key of the record is stored in the parent vertex node. Then the hash of the root vertex is stored in the block header, as mentioned, and used as a starting point for the search, for finding other tree vertices in the database, which allows for an efficient traversal of the entire tree. So in order to find data item which is in the leaf of the Merkle Patricia tree, we start from the hash root, and then we go to the database, and at each level of the tree we find the right node, which should be like another entry, another record in the database. So the traversal would need to look at the number of entries which is which is the height of the tree. Now we have state tree and the storage tree, and I'm going to talk about both. So in the state tree, each leaf corresponds to an account in Ethereum. And the key string for the account is derived from the hash of the account address, while the value of the leaf includes the balance and the root hash for the storage tree of the account. So why do we need two trees and two levels? Because the first level is different accounts, and the second level is how we represent the data, the state of one particular account. For the storage tree, which is the tree for representing the data of one particular account, each leaf represents Ethereum data for a given account or a given contract. And the key string is derived again by the hash of the contract address, while the values reflect the data model described in the Ethereum contract. And an updated state of an Ethereum account is retrievable by traversing the storage tree vertices in the level DB database. So let's take a look at the visual representation. So these are blocks stored on a file. And this is a header in the usual. And then block body with transactions. Okay, so this header is stored in the database, key value store. And the body but separately. Okay. Now these are records corresponding to one node in a tree. Node in a tree. So state tree. We start from the state root hash. Now we want to find the right account, the entry, the record in the database that corresponds to the right account. So we do the traversal. We start from the root hash, which points to the record in the database. And then point in the database would point to a branch hash, right? So like the hash of one of the branches. So this is how we find the right branch. And then from the branch, we go to the leaf, right? So there are two leaves. In our corresponding to two different accounts. Now, the leaf record in the database corresponds to one account, and it stores the root hash for the storage tree. So now from the state tree we can start traversing the storage tree. And the storage tree would be would start from the root hash, and would similarly go to one of the branches, and then we have the leaves. And in the leaves we have some specific information related to the storage of data in that particular account. And similarly, we have a tree for receipts, and we also have a tree for transactions. Okay, so here you see a different representation, but it's similar. Maybe it's easier to understand this way. There's here we have Patricia, state Merkle Patricia tree, and here we see the tree itself, where each node, each node or each vertex in the tree is a separate record in the database. And see the balance. We can retrieve the root hash for the storage, which points to the root of the storage Merkle, by which we can also traverse and get to the root. And in the leaf, we can find individual variables. So imagine you are writing a program, particular smart contract, and the program includes several variables. So we have each of the variables, and each of the variables can be updated over time because it's part of the state. Okay, so that program would be deployed for a particular account. So in order to fetch and update the value of the variable in the program, we need first to find the right account by traversing the state tree. And then we need to find the right variable for that account by traversing the storage tree. And once we find the right variable, we can retrieve its value and update the record or the record in the database. Now, Ethereum, okay, so that's the view for one block, and that's a view for a different block, right? So how does it work in Ethereum? In the sense that, okay, suppose we have two different blocks, and the state has changed from one block to the other, but not everything in the state has changed. Just some of the variables in some of the accounts have changed. So does Ethereum need to replicate everything for the new block? Even the records that have not been updated? The answer is no. Ethereum is applying very smart copy on write technique in order to save on the space. So how does Ethereum do that? If the same account has not been changed from the old block to the new block, then what happens is that the pointer in the new block would still point to, like here, like in this example. You can see that there is a pointer from the vertex in the Merkle tree, the new block, which points to the vertex in the block. Right? So you can see 2 points point to the same vertex. This vertex has not been updated between the blocks. On the other hand, this account has been updated. And as soon as it's updated, only then the new record is created for the new value of the data in the account. And the same technique, copy on write, is also used for the storage partition. So here you can see that one variable, it has the same value in the old block, then the record for the variable would not be duplicated. But the variable 2 has been changed. Then a new copy of the record, the new value. And what happens now is that not only are we able to answer the question, what's the state of the most recent block, but we can go back to history and know the state for each of the blocks in the past. So we take some historic block, and we can restore the state of that particular block even today. So it's relatively expensive, but because of this optimization, copy and write, it becomes much cheaper. So that's the last slide in the first lecture on Ethereum. The second lecture would be dedicated to smart contracts. And as usual, questions are welcome. Thank you. Slide number 14. Yep. Yes.
So when you delete, you are tampering the data, right? So
I am not, well, so when I say deleted, there is a transaction which deletes the account. So instead of eliminating the data, I add the transaction which says now this account is inactive.
I'm not getting the deletion means you are adding.
It's a deletion of an account. Imagine like, okay, you open an account in the bank, and then you close the account in the bank. So now the account is inaccessible to anyone, including you. However, the bank still keeps the record of the account. The bank knows that the account was first opened and then closed. So the same here. A ledger is a log of all transactions. So in the ledger, people would be able to see this account was opened, created, and then this account was deleted. So we do not delete information from the ledger. We just make the account inactive. Of course. I understand. So you still, like, the ledger is still